So in the previous videos we have discussed fluids when they are the pressure and the Pascal principle, which is about incompressibility and transfer of forces in fluids, and we've also introduced the ideas of buoyancy and flotation and Archimedes' principle. In this video we're going to introduce the continuity equation and the principle of Bernoulli's principle, which is form fluids in motion, because everything we've seen so far has been fluids being stationary, and now we want to describe when fluids are moving, because many instances like a river or like a faucet open in the kitchen, the water falls. Why does the water come from the ground if we're living in an apartment complex? How does it come to the third, fifth floor, whatever, right? So we need to be able to describe that the water is moving. And so how do we describe water in motion? Those are the things, or some of those ideas, because water in motion is very difficult, very early, very soon, becomes very, very mathematical. So we're gonna just get some ideas, some principles that are gonna allow us actually to qualitatively, at the very least, understand the world of fluids, right? So the first idea we're going to discuss is what's called the continuity equation, right? So here's the idea. Let's say that we have, for instance, a syringe, and the syringe goes like this, right? And I push the plunger, and I'm just observing how much, let's say, we collect in here. Right, let's make this even more obvious. So let's say this is a beaker or something. This is like a huge syringe or whatever, right? And it's filled with certain volume. It has filled with certain liquid, and I start to press the plunger, right? So I just press the plunger in here. So what do I observe with the fluid? I observe that the fluid starts to lift because the fluid is incompressible. So if I put the finger and I try to push, I cannot do anything. We're assuming the fluids are incompressible. They are pretty incompressible in reality, so that's a good approximation. And so we're going to be pushing, and nothing happens. But if I release, when I push, the plunger moves, which pushes the liquid, and some liquid starts to lift. And now one thing that obviously we know is that if the liquid was all the way up to here, let's say, went from here to there, and this says this is 5 milliliters, or yeah, let's say that's 5 milliliters, excuse me, and this is 4 milliliters. So what I observe is that the syringe has moved from 5 to 4, so the plunger is going to be now in there. And so how much liquid would I expect to observe in here if I'm also having measurements of milliliters? Well, I would observe that after I push here, I have 1 milliliter, and obviously this is trivial. Well, we're trying to see what we can conclude actually from this thing, because if you realize over here the area is the same, and so if I push I expect, but what's going to happen in this section where the area decreases? That's the idea for the continuity equation. Now obviously this follows from the fact that, as we were saying, the volume in needs to be the volume out, right? So whatever I have, if the volume cannot be, whatever I put in needs to be the same volume as the volume out of the system. We kind of expect that. But let's see how the volume behaves in two sets of the cross of the syringe. Let's make this diagram, and this diagram represents that. And let's imagine the plunger was here, and then it's going to be moving here, and it has displaced delta x1. The area here is A1, and we're going to observe what happens to the liquid that used to be here, but then it's going to end up, let's say, all the way in there, right? Because it's just displacing that. When I push here, this thing moves to all the way and then eventually falls. So how much does it move? Delta x, right? I'm saying if I push 1 milliliter, 1 milliliter needs to, I find 1 milliliter, which of course is the 1 milliliter that came from here. So what I'm saying is I'm going to push this much. This is the mass that's going to lift. And of course I expect that then the volume in there, the volume in, let's say that I push in, that's going to be the area times the displacement. But the volume out is going to be the area times the displacement. And what I expect is that the volume in needs to be the same as the volume out, because again, the fluid is incompressible. So if I push it here, this much lifts. Now I'm interested in knowing the flow, right? Which is how fast, V is flowing. The volume, how fast the volume is flowing. So how do I do that? Well, what I can observe is just simply calculate the change in volume over time. That would be kind of the flow, right? We can call flow Q, but I don't want to call it Q. We're not going to call it in this class, because Q, we're going to save it for heat, but sometimes you're going to see something like Q. And so if I do this, what I'm observing is that I can just write that volume in is volume out, so that how fast the volume goes in is how fast the volume of the fluid goes out. And so let's continue over here. I can just write A1 delta x1 divided by t, it's equal to A2 delta x2 divided by t. But how much is delta x 1 over t? Well, that's the velocity, which we're going to call like this special v1. And how much is delta x2 divided by t? Well, that's going to be the velocity 2. And so what I can observe is that if I replace those, I have is that the A1 times velocity 1 needs to be A2 velocity 2. This is what we call the continuity equation. And it's an interesting thing. The larger the cross-section, the slower the fluid is going to be flowing. The smaller the cross-section, the faster that the fluid is going to be flowing. This is the first principle, which is the principle of continuity equation, which follows from incompressibility of fluids and also conservation of matter if you wish, right? So first idea in here, flow of volume. How much push is how much it gets out. How fast it goes in needs to go how fast it goes out. From that, we extract this equation, which is going to be very important to observe or to study Bernoulli's principle. The second part we want to see in hydrodynamics, which is fluids in motion, is Bernoulli's principle. And the idea here is like, we're going to observe, let's say that we have a pipe with a certain cross section, let's say A1, and it just follows some liquid, and then we see that the pipe goes up, let's say, and we have an area A2. And let's pretend that the pipe is above the ground to make the more general case possible, where this is height H1 and this is the height H2, or Y sub 2, excuse me, right? Y sub 2, where's the position of that? Y sub 2, right? That's Y sub 2. And then I say I want to analyze what's going on, and there's flow, let's say, going in this direction. Okay? There's a first idea which we can discuss in here, which is Bernoulli's principle, the most elemental way, says that wherever velocity is high, pressure is low. And conversely, wherever pressure is low, velocity is high. Wherever velocity is low, pressure is high. That's basically how we enunciate the principle of Bernoulli for applications. From this, we're going to be able to see all the applications, right? Whenever the velocity is high, pressure is low, or whenever pressure is low, velocity is high. Let's take this piece of pipe, right, as we were making before with the continuity equation, and let's see what happens in here. Let's say that there is net flow going in here, right? So the fluid is flowing that way. And so what we said is like if I have, and let's say, by the way, that in this case, let's say also that in this case velocity here is, oh, we obviously velocity here if this cross section is smaller, this needs to be higher, right? So now velocity here is faster, right? So velocity in, velocity out, faster. So now I have what? I have a change in velocity. So therefore I have a situation when there is a change in velocity. When there is a change in velocity, we know there is an acceleration. If there is an acceleration, there is a net force. And so if I have a net force, and pressure is defined as pressure over area, force over area, now I'm going to have a net force F1 in here, right? And I'm going to have a net force F2 in here, right? Or in other words, I'm going to have also a pressure 1 and a pressure 2. And here's the thing. I know from here immediately that if the force net needs to be like this, and I have a force there and a force here, right? I need to have a net force, let's say, going that way, whatever force is pushing the liquid in this direction, and whatever the pressure that this liquid observes in here in this direction is the same as this one, right? And so what I'm going to observe is to have a net force P1 needs to be larger than P2. Why? Because when I'm applying the pressure in here, that's going to be a force divided by the area, that needs to be larger than this one, otherwise I wouldn't have a net force. So what I observe over here is that the velocity is going to be higher, the other way, that the velocity is going to be slower. To accelerate that is because I have to have a net force. The net force is going to be the difference between pressure here and here. So P1 and P2. The difference between those pressures is the one responsible for the net force, which is the one responsible for accelerating the fluid so the fluid can move faster. And this is the idea for the continuity equation, the first thing that we can see from Bernoulli and see it here. But Bernoulli can go beyond, because Bernoulli is allowing us now to make a conservation of energy argument for how fluids behave. In chapter 5, we introduced the laws of conservation, and we studied the law of conservation of momentum and rotation, that we said, oh, momentum, whether it's angular momentum or linear momentum or translational momentum, is just simply a quantity that we call is the amount of motion. And then we introduced another idea, which was the idea of energy, which we will revisit very soon in the next chapter, in thermodynamics, which is the idea that the energy is also somehow an accounting or bookkeeping approach to physics, where we're saying the amount of motion is associated with this, and then we're going to be generalizing this idea of motion, because motion doesn't need to be necessarily just actual motion, which is kinetic energy, but can also be potential motion, and we call that potential energy. And so how does this work in here in fluids is what Bernoulli's theorem, actually, Bernoulli's principle is actually going to tell us. So in this case, first of all, let's analyze what's the situation in here. I'm going to have a velocity here, and I'm going to have a velocity in here. And of course, being a stretch, narrower, velocity here needs to be higher. So what I observe is I can just say what's different between the initial and final conditions in here, okay? So let's do this. Initially, this point has what? It's going to have kinetic energy, and it's going to have potential energy. And this point is going to have what? Kinetic energy and potential energy, right? So we can think that our system now is, let's say, a certain volume of fluid that we're going to follow through the pipe and say, hey, the fluid has gone from here to there. The apple has gone, or the marker has gone from here to down there, or from down up, right? So we're going to observe is now what's changing there in terms of energy. And we're going to discuss that for fluids. So I have an amount of motion in here which is moving with this velocity, so it's going to have kinetic energy, and it's this height, so this has this potential energy, and it's going to end up in here with a certain velocity, so there's going to be another kinetic energy, and a different height, so another different potential energy. And so what I can see is that, as I know from previous chapters, if I calculate what's different between here and final, initial and final, if there is any difference, that needs to be because there is work. So let's calculate what is the difference between kinetic energy and potential energy. To begin with, let's analyze the final minus initial, right? So let's say the total energy at the end, which is going to be 1/2 of the mass. Well, let's first rewrite this thing in a kinetic energy. That's 1/2 of the mass of velocity squared. But we don't like to work with velocities. That's going to be mass 2. And the amount of mass is the same because we're following the same amount. Okay, so we don't want to work with mass, so we're going to have to say 1/2 rho, which is the density of the fluid, times the volume of the fluid, times velocity squared. What about the potential energy in this case? Well, potential energy in this case is going to be the mass times g times the height, and the height is going to be whatever the height it is, which is y1 or y2 in there, okay? But again, in this case, we don't want to use mass, so we're going to have to write rho, the volume of the fluid, g, and the height, which we can call the y, okay? And so now we can write all the difference in kinetic energy between here and there, and let's say we're going to have, if you make the numbers, you're going to find that this is 1/2 mass 1/2 rho, the fluid is the same, so the difference in kinetic energy is just going to be 1/2 rho fluid, the volume is the same, the only thing is going to be V2 minus V1, and this square, right? That's going to be the difference in kinetic energy. So when I subtract energy at the end and at the beginning, I'm going to have 1/2 rho f, volume f, the difference in velocities. When I subtract the potential energy beginning and the end, at the end I have y2, at the beginning I have y1, but it's still the same fluid, the same volume, and then it's going to be the same gravity, of course, and now I'm going to have y2 minus y1, or obviously delta y, okay? Very good. So now the difference in energy is going to be 1/2 rho of the fluid, volume of the fluid, plus y2 minus y1. So this is the difference in energy. And now I say maybe the energies are all balanced and we're all happy. But what if this is different from 0? Well, if it's different from 0, meaning if there is no energy, the energy is not being conserved, it's because there needs to be work. And what's that work? Well, work is always a force times a displacement. So let's figure out this one quickly, and let's erase here and let's write, because we're trying to focus now on what is that work in terms of the fluid. So now we're going to analyze what is the work done on the system. So it needs to come from the outside. Remember that the conservation of energy says that the change in energy is equal to the force, which is going to be external force times the displacement, right? So we need to find what is the external force. Well, we have a force that is pushing the liquid in this direction, which is going to be inside the system, right? That's going to be the force 1. And we're going to have a force 2, which is not going out. It's going to be coming in the system. Why? Because we're trying to find the work in the system. Okay? So if we analyze that work, finally, we need to analyze the work is done in here and the work is done in there. So we're going to observe that this is going to be F1 delta x1 plus, let's say, minus F2 delta x2. But we can go back to the analogy that we made before and say, how much is the delta x1 moved in here? And this is the delta x2 moved in there. So what I can do then is I can multiply delta x times the area is going to be the volume. So if I divide the force by the area, I have a pressure. So what I can do is just multiply and divide by the area, and so I have force over the area, and I have delta x1 area 1 plus, let's say, or now we can just write the minus, the force 2 over the area delta x2 area of 2, right? How much is that? That's the volume of the fluid. How much is that? That's the volume of the fluid. How much is that? That's pressure 1. And how much is this? Pressure 2. So how much is work? Well, that's going to be volume times P1 minus P2. And we can then bring back the idea that we said that the change in energy we found was the same as the change in kinetic energy and the change in potential energy. So we can just write everything. Let's save this space for the final. Okay, and so we're going to say that this is the same as the change in energy. So that needs to be the same as 1/2 rho volume times V squared minus V1 squared plus rho volume G Y2 minus Y1. And what do we see? We have volume and we have volume, so we can cancel that and that. And so what do we observe? That we have the difference in pressure. So I have P1 and I have -1 and -1. So I can bring all the 1s to one side and all the 2s to the other. And so I can say that 1/2 rho volume, not anymore volume, this cancels, right? V squared 1, which is the kinetic energy of 1, plus rho G Y1, which is the potential energy in Y, plus P1 needs to be the same as 1/2 rho v squared sub 2 plus rho v rho g y2 potential energy of 2 plus, or the term that used to come from potential energy plus the pressure in 2. So now I have an equation that conserves the energy. At the beginning I had certain kinetic energy and I had certain potential energy. At the end I'm going to have certain kinetic energy and some potential energy. But if they're not the same, it is because there's work. And the work is the result of the pressure. So here I have pressure and pressure. So now I can just put everything in here and just say this needs to be conserved because this is for any case. If there is no difference in pressure, then what happens is that the velocity becomes potential, which is the same as when I throw this upwards. It reaches the maximum and then it falls. But if I want to achieve more than that, if I want to accelerate that, I need to have a net force. So I need to have a pressure here that's going to be compensating for that. Or I have to have a pressure here that's going to be producing that. So I need to have a difference in pressure, basically. So then I can rewrite everything here by just saying that 1/2 of rho velocity squared plus rho g height plus the pressure needs to be constant. And this is the general principle for Bernoulli. If you want to analyze Bernoulli at any point in the pipe, any point, all over the place, this needs to be introduced. And this is conservation of energy, but now for fluids. So I still have rho, which is for the density, and rho, but it's kinetic and potential, but now I have a new term, which is the term due to the pressurization of that fluid, because I'm going to be able to put the fluid, and that pressure, of course, is going to be acting the same way we're saying, right, with the pressure that we observed, excuse me, the pressure that we observed before, right? So from this equation, we're going to be able to analyze, hey, how fast something is filling a room, but also why airplanes fly, why you can sail with your boat, why, excuse me, the shower curtains get to you when you turn on the faucet, right? Simply stated, whenever velocity goes high, pressure drops. Let's say that we're in the same height, we remove potential energy. If velocity increases, and this needs to be constant, and this kinetic energy plus pressure, this needs to lower. So whenever this is high kinetic, I achieve high kinetic with low pressure. If I want to have high pressure, I need to reduce kinetic. High pressure with lower pressure, because we're at the same height. Of course, you can complicate that more by adding a height, right? But then you have to count also for the potential energy. But at the end, we're just analyzing how energy is conserved for a fluid, which is beautiful because it was easy to see for a particle, but what about with a continuum medium? How do we observe that? Well, we observe it thanks to this idea of density. We said it's going to be convenient, extremely convenient. We have been seeing it all along, but we're going to be able to track how fast it's moving, how high is going in atmosphere of, excuse me, in the world. If it was not in the world, this term would be missing, right? But we still have conservation of energy, and finally, some pressure term in here. That pressure is going to be the one that's going to be allowing us. So if I want to accelerate a liquid, what do I have to do? From a certain kinetic energy to some other higher kinetic energy, well, the pressure is going to have to be lower, so such that there's actually net, and so it's actually accelerated. It makes sense, we just saw that, but this is just the explicit explanation, and more complex because it includes other scenarios where you're changing, as we said again, velocity, height, and pressure. Just one last thing that we can mention in here. Sometimes we get confused about this idea because we're thinking of pressure not just as what pressure is, but I'm thinking, hey, if I have a faucet, excuse me, if I have a hose and I put high velocity, have a high flow, right? So, or the water goes faster, right? It hurts me more if the water goes faster than if it goes slower. So I feel a higher pressure, but this is because you're talking in your hand. What we're talking in here is what's the pressure that the liquid makes on the sides of the container, because again, the liquids apply the force in every direction at the same height. So the force pushing in the wall, right? So that's the sort of pressure we're talking about in here. We're talking about pressurizing a container. So that's an important thing not to get confused. Once you understand that, then just, yeah, okay, whenever I have high velocity, low pressure. And again, even if it takes you longer or you actually don't see it immediately, you develop a new intuition based on this, excuse me, the more that you practice, and that's where we're going to be doing problems. But again, it's important, once we have derived everything mathematically in here, there's no question, let's say there's nothing that we say there's nothing wrong, then the conclusion, excuse me, conclusion is going to follow from the premises, right? So we have followed the old logic, there's no invalid logic, there's no invalid premise. This is the conclusion, let's follow it. And then we can use this to understand many different events, as we were saying. For instance, how does an atomizer work? How does an airplane fly? Why can you just go with your boat against the flow of the wind, right? You're going against the wind and say, hey, how is that possible, right? And all those things. Okay, so that is because of this. Whenever I have high velocity, I'm going to have lower pressure. Whenever I have lower velocity, I'm going to have higher pressure. Problem number 12 in discussions said that there's an air duct that goes to a room, and the room is 8.25 meters and 3.5, let's say 3.5 meters, and this is going to be, let's say, 8.2, and it's deep 5 meters, right? And so the question here is, how fast does the air flow such that every 12 minutes the entire room is displaced? And so we can understand that obviously there needs to be somewhere like a ventilation or whatever, right? So it's pushing it, so we're just replenishing the room. So this is the flow of air. So how fast is it flowing here? So such that every 12 minutes we have it. Well, this is kind of trivial. We just said this is the flow of fluid. It's going to be, excuse me, we said we were going to call it. So there's going to be the flow, right? And the flow is just going to be how much volume or how fast the volume goes in time. What is the volume? Well, that volume is going to be 5 times 3.5 times 8.2 divided by the time. And time is 12 minutes, but that doesn't make any sense. So we can just say kilometers per hour or whatever you want to say. You could do it per minute. Let's keep it a minute if we want, and then we can always convert. So that's going to be what? Let's use the calculator. So that's going to be approximately equal to actually 12 cubic meters per minute. Now you can convert because you know the 1 minute is 60 seconds, so you can convert it to 60 to seconds divided by 60, and so you're going to have 12 divided by 60 meter cubic per second, which of course is 0.2 meters cubic per second. And if this doesn't tell you anything, maybe it's convenient to transfer it to liters. And remember the 1 meter cubic 1 cubic meter is 1,000 liters. So that means that that's going to be 200 liters per second. So now that makes a little bit more of sense. And this duct tape, well, more sense, let's say that we can appreciate how huge that is, because every second this duct tape is flowing in 200 liters of air. So imagine 200 of the bottles of 1 liter, obviously. If it's 2 liters, then it's 100, right? But like the small Coke cans, not cans, the small bottles, typically half a liter, bottles of water and Coke and so forth. So that will be 400 of those every second. And if you want to consider it in terms of cans, cans are 33 centiliters, which is going to be 1/3. So that will be 3 times that. So it will be 600 cans every second flowing in of air, right? Of air, but anyway, of air coming in. So that's how fast this room is displacing this fluid. Why? Because every time it's pushing the fluid, some fluid, let's say it's going to be going out, we're taking the air just to be able to live. So there's not going to be pressurization, it's just going to flow. And so the idea here, every 12 minutes, the entire room gets redone, refreshed. That requires a pump or well, you would have a pump to pump the air, but anyway, you're going to have a flow of 200 liters per second. Sometimes you might see that from here, so you might see that some people, that this is read as CMS, right, which is cubic meters per second. In America, it's very common to see the CFS systems and things like that. That's cubic feet per second, right? So those are different units. Now you would have to convert from meters to feet, and then you would have CFS. So some flow, if you go to Home Depot or Lowe's or whatever, one of these hardware stores, and you're trying to find some fitting or some hose or this and that, right, you have to figure out, or a pump, for instance, you're going to have a air pump for the system that you're installing, or maybe you want one for your garage to work with your power tools or whatever, right? So you need to find a flow. The flow is sometimes CFS, that's cubic feet per second. Now you can make sense because you can see how many bottles it's going to be filling every second or things like that. Right? You have now, if you go in liters, not with cubic feet per second, I have no clue about that. But basically just different units, but we're seeing how fast something is flowing, in this case to fill the room. Let's see another example. So one thing we can add into that problem, by the way, is if we say that the flow is, this being volume over time, is 0.2 meter cube per second. Now something that we can do is just see how fast the fluid is actually flowing in. So that will be like the flow, but we might actually want to see what's the velocity of the air coming out. So how fast is the air blowing in to actually achieve that thing of refreshing the room. And of course the volume is given by the area times length, right? So if we take the duct tape, let's say, duct tube, so we're saying that the air is being pushed such as this volume, this small volume, that's going to be a certain displacement, right? So that's going to be this, we've seen that before. So this volume is actually, that volume display is going to be the area times the delta x. So if I replace in there, so what I'm going to find is that the volume divided by the time is going to be the area delta x over time, and we have seen this already. This is of course the continuity equation. And so now we can find from here that this needs to be 0.2 cubic meters per second. So what we can do if you want to find the velocity is just simply take 0.2 cubic meters per second and divide it by the area. And in this case the duct tape is 12 centimeters radius. So this now, the radius is 12 centimeters, which is 0.12 meters. And so the area is going to be pi 0.12 squared. And if you make these numbers, 4.4 meters per second. So to actually generate this flow through this duct tape, we would have to have this velocity. So in this case, it's problem number 13. Right, problem number 13 says there is what is the volume rate of flow of water from a 1.85 diameter faucet. So we're going to have a diameter of 185 centimeters. So that's going to be 0.925 radius. And that's going to be 10 to the minus 2 meters, right? So we go directly to meters. If the pressure head is 12 meters. So what does this pressure head mean? So you can imagine something like this. Of course, nowadays we have pressurized lines at home and all that because we have pumps and we're building it anywhere anyways, right? And so we have a water pump pumping. But in the old days, let's say we would have something like a water tower, which is the one responsible for the pressurization. And so the faucet will fall, and then we would have here our faucet having air. So this is actually the height we're talking about, which is 12 meters. It's another way of saying that the pressurization is that equivalent of having that mass 12 meters high. So how do we solve the flow? Right, eventually we now know the volume over the time. We know that obviously the volume over the time is going to be the area times the velocity. So if this is the same thing we just discussed in the previous problem. Volume is area times displacement. So volume is going to be area times the displacement over the time, and of course that's the area times the velocity. So now if we want to find how much is the volume flow, we actually need to find the cross section times the velocity. Cross section we can find from here, but what about velocity? So the problem in reality is actually asking how fast it's going. From that multiplied times the area, you have the flow, right? The volume flow. So we can start analyzing this problem, and we analyze as anything in fluid motion through conservation of energy. And through, well, with everything that we do, so in the case of fluids we do. And that's Bernoulli's theorem, right? And so we're going to have to say what is the pressure, what is the energy here, and what's the energy in there, okay? So we're going to have to write the initial and final, and both need to be the same. So we're going to say is the velocity in here, the pressure in here, that was going to be pressure 1 at the head, and the velocity 1 at the head, and also the height 1. And the height 1 is going to be, or the y1 if you want to call it, it's up to use, the one is 12 meters. And so what about the faucet? We're going to have the height of the faucet, we can take that as 0. We could take this to be 1 meter, but then that's going to 12 meters above us, so that will be 13. Again, this is the origin of potential energy. That's why with potential energy we say it's mg delta y, because we have to choose a reference. If we choose the faucet as the reference, all the pressure is just the pressure up to there, which is the 12 meters. So we can take this to be 0. What is the velocity to, which is actually the one that we're trying to find, and what is the pressure to, also we're going to have in there. So how do we solve that? Again, Bernoulli theorem. So it's going to be pressure plus 1/2 rho v squared plus rho g height needs to be constant, and that is Bernoulli's theorem. Let's start applying numbers. I'm going to say that the situation at the beginning, this here needs to be the same as this in there. Now let's write this thing. Pressure at the beginning plus 1/2 volume velocity 1 square plus rho g height 1, and that's going to be the pressure out plus okay, from here we see directly this cancels because this is 0, and the velocity here at the beginning is 0 because we observed that the watering tower is just stationary. So this kinetic energy is 0. Second thing we can observe, what's the pressure? Well, the pressure here is open to atmosphere. If the faucet is open, then the pressure is 0. And so this pressure is going to be 0. But the same can we say about this one. So because that's also open to atmosphere. So if we have a water tower, the water tower is open to atmosphere, it's not pressurized. It's just the only pressure comes because of the height of the liquid. So this pressure and this pressure are going to be 0. And so we're going to have 0, 0, 0, and we have rho gh equal to that. So from here, we're going to be able to solve for velocity. So if we try to solve for velocity, rho and rho cancel, and so I have that the velocity of 2 is going to be equal to 2 times gh1, which is going to be the same as 2 times 10 times the height, which is 12. And that's going to be the square root of 240. That it's about 15.5 meters per second, and so we can just go back and say how much is going to be the flow. The flow is going to be the area times the velocity, and that's going to be the area is going to be pi, and the radius is square. Don't forget the units, but that's a 2 square times 15.5. And if we make these numbers, we find the flow to be 4.1 to 10 to the minus 3 cubic meters per second. So important to solve this is not the math, which is trivial, it's just to observe step by step what is the physics applied in this problem. What is the pressure that's acting on here? This is water which is left to itself. Well, you could always say it's atmosphere, but if you put atmosphere here, you put atmosphere there, right? So in this case, we use gauge pressure directly, and that's fine. So we're gonna have the same pressure here than here, and so this water is just having pressure, it's just applying pressure, let's say, because of its own weight, which is this one over here, right? So what's gonna be observing is just up, is gonna be moving, potential energy is going to be converted, in kinetic energy. It's going from up to down. It is not pressurized, the system, it's an atmosphere here and there, right? Once you open this atmosphere, so the pressure in there is an atmosphere, inside the system is going atmosphere, right? What's the pressure in, what's the pressure in there, right? Remember that pipe that we made, the pressure in here, that's just atmospheric pressure, pressure in here is just atmospheric pressure. So that's just atmospheric pressure, so you can take that to be 0 or just cancel it with each other. Because you could have taken this to be non-zero, right? And then we could have done that. If that is confusing, let's say P1. Then we would have over here, we would have plus P1 minus P2. But the question is here, is there any net force? No, this is just open the faucet, so it's just letting it go through gravity, so there's no extra work done in here. So these one are going to be the same, so this is going to be cancelled, right? That's another way of saying that. So then eventually we have the same result. And so the entire thing is you observe this equation, this reminds you a lot to that of what's the velocity of an object when you let it go. It's just purely due to the height, which is the same case here. Another story would have been if we had a pump here pressurizing the liquid, or a pump here just to extract it or something. But that's not happening here. We just open the atmosphere, we have the same pressure that's going to cancel. That's the first thing. Then observing the height and observing the kinetic energy is the same. Why do we say the velocity here is 0? If you observe the tank is not moving. So yeah, you could say, as the liquid goes, this needs to flow. But yeah, it's going to be flowing so ridiculously slow that in the first approximation, you can take that to be 0. If the tank was very small, then yeah, you would have to consider that. But that's not the kind of example that we're talking about. If we're talking about the tower, a water tower, right? That water tower is going to have a huge volume for the amount of volume that you're getting out. So at every single instant, the velocity here is going to be negligible in comparison to the other one, so you can disregard the one. And the last thing is just seeing the height, so we can take that to be 0. If you don't want to take it to 0, take it to whatever you like, 1 if you want, but then this is going to be 12 meters above, because the entire pressurization of this system is achieved through putting something high. So that's why if you take a bottle and you put a hose, it flows there, but if you put the hose up and the bottle down, it doesn't flow anymore. Now you would have to, for instance, push. So you would have to add a pressure so that the liquid is capable of that, because you need to conserve energy. So now I don't have potential energy. So what potential energy I'm going to convert into kinetic energy. The bottle is stationary. There's no motion of the water in the bottle. Now I want to push. If I push, then I have pressurized. So the thing is just going to have some non-zero plus this 0. This is actually going to be non-zero in that case, because we have to convert, and this needs to be non-zero. So then I'm going to have to achieve that through pressurization. That's why I need a pump. So I need just to pressurize that. When I pressurize that, then I can achieve that. Excuse me, that effect. So this is, again, it's just conservation of energy. So just see the situation and observe everything what it means. What is the pressure? What thing is acting on the system doing work? In this case, the pressure is doing work, which is why we derive a Bernoulli theorem, right? Because conservation of energy when external work. If there was no external work, then it's purely kinetic energy becoming potential. It's like dropping an object. It's the same. But now we're having it with liquids, right? And with fluids. So that's why it's interesting, because we have naturally the idea of work in the system. The idea of work in the fluids is done through the pressurization of things, which will be achieved with a pump. And in this particular case, we don't need it. It's just simply the water tower. If the pump was off, let's say that could be like a supplementary system or something like that. But anyway, converting potential energy of the fluid into kinetic energy of the fluid, Bernoulli's principle. Let's see another example. So problem number 39 in discussion is a nice one, because we have now an airplane. Let's say that there's an airplane traveling, and this goes like this. Wow, it's kind of a weird airplane. Okay, and the airplane is just traveling there, right? And so we're gonna extract the cross section of the wing, and we can probably draw something like this, something like that. I don't know. And that's gonna be a cross section of the wing, right? And so we're gonna observe as the air is coming, the air is gonna be displaced, and so air is gonna be moving at different velocities underneath and above. And because air is moving at different velocities, wherever the air is moving slow, pressure is high. Whenever the air is moving fast, pressure is low. So that's going to generate the net pressure vertically, which is the one that gives lift to the airplane. So the airplane needs to go fast enough such that the geometry is distributed such that it actually has the lift. Okay, very good. So the idea here is that the wing of the area, of the wing is 88 square meters. And the air passes over the top at 280 meters and 150 meters per second, right? So because the velocity of this one is lower than that one, then we're going to have a situation where the pressure here is going to be higher, right? Velocity is lower. So because velocity, we can write it here, because velocity in 1, which is on the bottom, is smaller than velocity 2, then the pressure in 1 needs to be larger than the pressure in 2. And so I'm going to have a larger pressure here than a larger pressure here. I'm going to have a net force pointing upwards, right? We're going to have a pressure here and a pressure there, so we're going to have a force, right? And so we're going to have a force in here, which is going to be pressure 1 times the area, which is going to be larger than the force 2, which is going to be pressure 2 times the area 2. The area we can assume is the same, let's say, right? And so I'm going to have a net force there, and that's going to be the force of lift. The airplane is going to be able to stay there. Very good. So how do we calculate that? In this case, we can just, the question is, by the way, what is the lift? So what is the net force, right? So we're going to have to find the difference in pressure, and that's going to give us times the area, that. So how do we calculate the difference in pressure? Is going to come through Bernoulli. So we're going to have a situation where we are going to have pressure change, let's say P2 minus P1, plus kinetic energy difference, which is going to be velocity 2 minus velocity 1, plus potential energy difference, which is going to be the height 2 minus height 1. We can take the heights to be approximately the same, so this is 0, and that of course needs to be 0. Now in balance, this is conservation of energy, and so we can solve for P2 minus P1, so we can have that P2 minus P1 it's equal to minus 1/2 of rho v squared 2 minus v squared 1. That's going to be, otherwise just write 1 and 2 and just work the same way. So let's make the numbers in here. So if we make these numbers, we're going to find the difference in pressure needs to be about 5.59 10 to the 4 pascals. But the question is not about the pascals, the question is about the force of the lift. And the lift force is going to be the difference in pressure times the area. We just said that in here, lift is the same as the difference between these two, so it's going to be F2 minus F1, which of course is going to be the pressure 2 minus pressure 1 times the area. And so if we make that calculation, we're going to observe is that the lift, well, we have a minus in here, so actually this should be minus, obviously, right? It's minus. So obviously P2 is smaller than P1, that's why we have net positive force, right? So that's going to be minus, so the delta P we have to define then as P1 minus P2, okay? But it's okay, that's a minus sign. At the end of the day, of course, make sure that it's consistent with your system, but just goes up. And so now we're going to have the difference in pressure times A. That's going to be that number times the area, and the area is 88 square meters. So we're going to have to multiply 559 10 to the 4 times 88 meters. And if we calculate that, we can find this is about 2 orders of magnitude more. So we're going to find something like 3.2 10 to the 6 newtons. So this is the lift that you have with this wing cross section and that. The higher the area, the higher the lift. So you need wings that are large area to have better lift that you actually have no wings. The problem, for instance, if you lose a wing in an airplane, is that you might not be able, and in fact, you're going to be able ever to compensate for that in commercial airliners. I think like jets produce enough thrust so not to actually need the wings in some cases, but that's accidental. Let's say it was not desired. So in this case of airliners, you're going fast, and so depending on how you adjust your angle of attack, right, you're going to have a control of the velocities of the force, and so you're going to have larger or a smaller lift. If you go like crazy, at some point your angle of attack is going to lift this what we call a streamline or laminar flow, and so you're going to have eddy currents or turbulences, and so you're going to lose lift and the airplane is going to fall, right? So those are things that pilots need to study. But now we understand if you change the angle of attack, then you're going to be distributing this, so the velocity here might be faster, and so you actually have higher lift, right? But at the end of the day, this is the lift that you have. Now, if you wanted to have something heavier, you would have to have a cross section which is larger. It will produce larger lift, right? At the same time, of course, larger wings will put more weight. And at the end of the day, what you're going to have in the balance in terms of the airplane, if this is your airplane, you're going to have lift and you're going to have the weight of the airplane. So given the velocity that you can go with your airplane on the air, which is given by the engine's performance, and given the particular geometry of your airplane, which is the model, the manufacturers, the engineers are going to write a handbook telling you this is the maximum weight that you can have, because if you overcome this load, then that means that you're going to have a lift which is not enough to compensate for the weight. You're going to drop, and of course typically you're not going to be able to take off in general, right? So that's going to be a catastrophe usually. So that's another idea in here, right? So we see why we have fluid motion, we can control the velocity depending on the angle of attack. That's going to generate different velocities, which eventually translates through Bernoulli principle mathematically we find into net pressure pointing up. In this case, if we take that pointing up, so that just was negative because it was this difference, which F2 minus F1. In reality, this is F1 minus F2 minus F1. F1 is positive, F2 is negative, and so that's why, right? And eventually we're going to have this force lift, which is 3.2. If you divide by times 10, that's going to give you the maximum mass that this object will be lifting with this velocity, right? Increase the velocity of the airplane also, you're going to increase also the velocity, so you're going to be able to gain a better lift, provided you obviously can't do that, right? And there are other effects that matter in terms of drag and this and that, right? And then you can sustain that much weight. If you have a smaller area, then you have a smaller area of the wings, you can sustain less. In here, then you could see, oh, this is the lift, so this lift is being produced on the wing. So then you would go and say, hey, how much stress does it suffer, or what's the compression, how much is the tensile or compressive stress on the wings, and then we use chapter 6, right? So everything is connected, and so you see everything we can use it to apply it, and if we apply it, then we're doing engineering. We're not doing physics. In physics, we're just concerned about the principles. Once we establish the principles and we understand the nature, let's leave to the engineers to figure these things out. But it's very interesting actually to see how they work. So it makes sense. Angle of attack, as you probably heard, as the airplane is taking off or landing, and the flaps, and also and so forth. Those are the systems that we can be using to control that sort of thing. Lift here is going to play the role, so to speak, of buoyancy in liquids, right? Because the mass displays of a gas, the gas is very low density. The other thing I mentioned is the density of a gas. We're taking it to be about 1.2, right? Remember, the density of water is 1,000, so you see it's about 1,000 times less. So that's why you don't really consider here the volume displaced. But that's another thing that you could consider anyways. And yeah, basically that's the idea. So now we're kind of having lift through the wings. Other way of saying this is not just through Bernoulli, but it's kind of physically, eventually you could say, I think it's debated still today, why airplanes fly. But another thing is just to say, oh, because I'm going this way, then I have air hitting here and air hitting here. And so the balance of force, action, reaction, the air hits the wing or the wing hits the air air hits the wing, air hits the wing hits the air hits the wing, and so we have the action, reaction into the wing, and the balance of that is giving you the lift, right? So it's another way of saying that. At the end, we're just providing analogous, or let's say equivalent formulations, but with Bernoulli we're using conservation of energy to observe why airplane flies, and you could see something similar with a sailing thing. With the sailing, how is the wind coming with your boat, and how you can make your sailing so such that you control the pressure here and there, velocity, of the air. If velocity of the air goes faster in there, that means you're going to have a net pressure going that way, which is going to be pushing your boat in that direction, right? So Bernoulli's principle, hydrodynamics. With this, we conclude this chapter.